Hello folks, welcome back to Dubious Engineering. We're going to get into oscilloscopes, a little bit about what they're useful for, doing some practical examples with them, perhaps even sort of show you the basics of how to set them up, and a few different types of scopes. Alright, let's get on with it then. Some of you might recognise this. This is an ACOMS 27 MHz transmitter. It's one of those digital proportional radio controlled transmitters for flying aircraft and radio controlled cars and that kind of stuff. Now, immediately, the bonus of this scope here is the fact that you can save the waveform. And then you can scroll around that waveform and you can look at it once you've saved it to memory. It's actually quite good because you can see here the dense sine wave is the 27 MHz carrier wave. And then we have these 4 little lumps and then another portion of dense sine wave, 4 little lumps. And effectively, this is the encoding of the proportional radio signals to tell your car to accelerate, decelerate, however many channels your receiver might happen to be. So it's quite nice that you can get in there and see that kind of stuff. While we've got this hooked up, let's get out of that mode and let's have a look at 27 MHz in real time. So here I'm just winding the time base up here and you can see this lovely sine wave on the screen. If you know what you're doing, you can bring up a little menu down here. Sorry, just adjusting the trigger level. You can bring up a little menu down here which tells you the frequency of the waveform. So ultimately it's looking at those peaks and those troughs and it's saying, okay, the average frequency of the waveform is this. So normally what you would do with an oscilloscope is you would count how many time-based gradicules there are. In this case it's 1, 2, 3, 4, about 5 time-based gradicules, and then you would use the time-based value, which is 8 nanoseconds, and then you would do some calculations and calculate the frequency. But actually, in this case, the scope tends to do it all for you, which is really nice. And not only that, but if you look at the voltage, the peak-to-peak voltage, if you look at the amount of gradicules there are, the divisions here for amplitude of the wave. Currently, you'll notice we are set to 10 volts per division, indicated just here. And so with 10, 20, 30, 40, 50, 60, around 60. And it's sort of waving up and down a little bit. And the scope itself is now giving us an idea of the voltage. It's saying it's about 54 volts peak to peak. Again, that's a really nice little feature to have. Especially when you compare it with my trusty old steed of a Tectronix scope. The DSO here, which is a 60 MHz, 1 gigasample per second scope, real-time oscilloscope. Again, 2-channel. I bought this on eBay. I think it cost me about 60-70 quid. It's not bad. The display's not as cute. It doesn't do the maths for you like the other scope does. Plus, I got it cheap because there was a knob broken, so I 3D printed a replacement knob for it. But yeah, the point of the fact of the matter is it does work. You know, it's just a little bit older now and a little bit sort of a bit slower and not quite so easy to use. Perhaps it doesn't have all of the features of the Hantek DSO. Now, another scope that I do have is this guy here, which is a Hantek 2D72. This is a handheld oscilloscope. It's quite a magnificent little scope, actually. And as you can see on the screen there, I've done a pretty in-depth review of this scope before. But as you can see on the screen there, you know, it's a reasonable scope. It's a little bit more of a fiddle to drive because you don't just have like easy time base and voltage adjustments on that particular scope. It's you know, it's handheld. It's much smaller, but very useful when you're out and about. It also has a built-in function generator. I couldn't help it and set all 3 scopes up to the same signal source, which is this 27 megahertz transmitter here. So here's the Hantek DSO 5202P doing its thing, and showing us that the frequency is around 27.17 megahertz, which sounds about right for a yellow band transceiver. Here's the Tectronix DS210 doing its thing. Again, very similar sort of waveform, all black and white. Not the most beautiful screen to look at, but you know, still functional, does its job. Again, it's a 60 megahertz scope, not a 200 megahertz scope. And then here is the little Hantek DuD-72 scope doing its thing. And again, it's telling us the frequency is 27.17, something along those lines. Quite cool, and that was literally just pressing the auto button. So let's press the auto button again, see if it comes up with a different grab of the waveform. Auto setting. Nope. There you go. It's quite happy like that. Let's auto set. Let's press the auto set on the Tectronix and see what the Tectronix does. Yeah, it's pretty good. Just need to adjust the time base a little bit to make that a little bit fatter, and then maybe just adjust the position of that waveform so the peak is in the center there, and then you can calculate out that frequency. And let's press the auto set on this guy and see what it comes up with. And there we have it, down the bottom here, 27.17 megahertz. Again, pretty good going. Very impressive from all 3 scopes. Let's try these scopes with a slightly higher frequency. So what I've got here then is a little handheld transmitter. It's a little Baofeng. I've set it to transmit on 145.500. And I've turned it on to low power, and I've put almost like a little tiny dummy load on the top of here, so it doesn't transmit very far. What I'm going to do is inductively couple that dummy load. Here we go. So the antenna is now sort of inductively coupled into channel 1 of the Tectronix scope and channel 1 of the Hantek scope. Let's fire this thing up and see what happens. Okay, let's just turn up the let's just turn up the volts per division and get the trigger level in a sensible place. There we have it. So the frequency says 145.9, sort of varying between 143 and 145, 147, yeah, around that sort of area. But we've got a good consistent sine wave on the scope here. Now, we also have the scope set to 2 nanoseconds per division. So if we just position that horizontally, there we go. Position that there. Okay, so offset it. And we can see up here, that suggests that is 6 nanoseconds to this point here. Let's just get that exactly where it needs to be. And that looks about right, 6.3 nanoseconds. So if we do the math then, so 1 over 0.0000063 gives us about 158 megs. That's interesting. So let's now move our attention to the Tectronix scope. Now, bearing in mind this scope is rated at 60 megahertz. There you go. Let's transmit and let's see if we can get any more out of the time base. No, we are on maximum time base, which is 8 nanoseconds per division. Clearly we go down in time base and we can't see a thing. But I'm actually sort of surprised that we even get this. That's actually quite good. Let's just adjust the trigger level there so the waveform is a little bit more stable. Position it. So we are 1.2 is a full wave. 1.2 is a full wave. So that's 1.2 times 8 nanoseconds, which weirdly works out to 9.6 nanoseconds. So let's get the calculator out, and again we go 1 over, that converts time base to frequency, 0.000009.6 nanoseconds. And actually, that's almost close, 104.2 megahertz. So I'm sort of impressed that this scope is still able, even though it's a 60 megahertz scope, it's still able to pick up more than double its stated range. That is quite cool. Well done, Tectronix, and also well done, Hantek. That worked an absolute treat. That worked out quite well. 144.9. So clearly, you know, it's these things are never going to be perfect over such a small sample range, but pretty impressive. And if we turn the time base down to 8 nanoseconds, there we go, and that's pretty much the same as what we were seeing on the Tectronix scope there. So here I am making a little tuned circuit, and what we're going to do is we're going to hit that tuned circuit with a specific frequency, and we'll find out what frequency that circuit is operating at by using a sweep frequency oscillator. If I had one, I'd love a sweep frequency oscillator. We're going to use a little oscillator, and we're going to see if we can excite this tank circuit that I've just built here. Included in the Hantek scope is a little wave generator, an arbitrary wave generator. I think that's what AWG stands for. So what we're going to do is set that wave generator up. We're going to sweep it through a variety of frequencies, connected across this little tuned tank circuit here, and we'll see what frequencies that tuned tank circuit responds to on the oscilloscope, and that will give us an idea of the tuning of this coil and capacitor. And this is the fundamentals of radio transmitters and radio receivers. Alright, so I'm hoping you guys can see this okay, but what I've done is I've set this up so I can press a button here and sweep the frequency, and at the moment I'm around sort of 30 kilohertz. So I'm sweeping the frequency now from 40 kilohertz, and we're going down 30 kilohertz, 20 kilohertz, and as you can see there's a sudden peak in the amplitude of the response. Effectively, that's where the tank tune is. That's where the tank coil is tuned. And you see if we can go too far in one direction. So let's just keep going. There we go. So 7 kilohertz, and let's just change the time base so you can see that a little easier. So this is now 7 kilohertz, and we get this peak that comes in at about 13 kilohertz, 14 kilohertz. Yeah, and then if we go past that 14 kilohertz, you can see that amplitude diminishing there. And that ultimately, what that's doing is it's telling us that this tuned tank is tuned to around 14 kilohertz. So again, another very useful little tool. And in fact, if we press the auto set button at this point, the scope is telling us quite clearly here, the scope is telling us that we're tuned to about 13.8 kilohertz, something along those lines, which also concurs with the value on the scope here, 13.75. Let's have another look. 13.775. So yeah, Smashing! There we go, and that's a little tuned LCR tank with a signal generator and a scope. What's he doing now, you might ask? Well, I am making a dummy load. I'm making a dummy load because I want to connect a large piece of ham radio equipment to an oscilloscope and show you the difference between amplitude modulation, frequency modulation, and that kind of stuff. I thought it would be quite interesting to have a look at it on the oscilloscope, and that's pretty much exactly what an oscilloscope is used for, is looking at waveforms. So I've got a PL259 here connected to one end of this cable, and the other end of this cable I have 10 500 ohm resistors. Well, they're actually 510 ohms. So ultimately what we're going to do is we're going to create a 50 ohm dummy load, and this will work on my radio, and it'll stop my radio from transmitting, and it'll also give us the opportunity to have a look at the waveforms that the radio is producing without actually transmitting on the airwaves, which is sort of important. Anybody that's going to be doing tests on any type of radio transmitter, you should probably have a dummy load that matches the impedance output of your radio transmitter. And in my case, the impedance output of the radio transmitter is 50 ohms. And there it is, folks. Just need to cut off the excess legs here, and we've put 10 500 ohm resistors in parallel, effectively creating a 5 watt, or something close to 5 watt, 50 ohm dummy load. So first of all, let me just show you how I've set up my radio. I've got a drill battery on the top. This is a Milwaukee M18 style drill battery with one of my power adapters on it, and that is plugged into a DC to DC converter, and this takes 24 volts down to 12 volts. At 30 amps this can operate at, which is really quite an impressive piece of kit. And then that is plugged into the power supply port on the back of the radio. Then I have my little dummy load here on its length of cable, and that is plugged into the appropriate antenna socket, which is the HF, or the high frequency antenna socket, on the back of the radio. So in theory we should now be able to turn the radio on. Happy days. The radio comes on, and when we transmit using the microphone, all of the signal goes into this dummy load here and doesn't go anywhere else. Now, we should also be able to take an oscilloscope and connect it to this and have a look at the waveform. So that's the next step. Alright, so I have checked that the radio is transmitting on its lowest possible power level, and I have connected the oscilloscope up to the dummy load. There it is. And now when I transmit on the radio, you should be able to see a signal come out on the screen of the oscilloscope. 1, 2, 1, 2. Now this is currently transmitting in lower sideband mode, which is very similar to amplitude modulation. So the amplitude of the signal will increase and decrease depending on how much modulation I put into the microphone, how much shouting I do. So you can see here then, in AM mode, when I'm transmitting and speaking into the microphone, there is always a carrier wave, and that carrier wave modulates ever so slightly. So when you're transmitting in AM mode, ultimately you're always transmitting a carrier wave. So it's not the most efficient mode of operation because you're always transmitting a carrier wave. Whereas with a single sideband mode of transmission, you're not transmitting any carrier waves. Now, let's have a look at FM. This is now FM mode, and what you shouldn't see in FM mode is massive amounts of carrier wave volume change. What you should see is frequency change, but the amount of frequency that it changes by is a very, very tiny amount, and it's very difficult for me to be able to show you that on an oscilloscope. Anyhow, I hope that's been a good bit of fun for you guys. It's certainly been a good bit of fun for me. Playing radio and reminding myself what an amplitude modulated signal looks like compared to a sideband signal, compared to a FM signal. Well folks, in case you hadn't guessed by the adverts that I've thrown down in this video, Circuit Specialists very kindly sent me the Hantek DSO 5202P, that's a mouthful, free of charge, in order for me to make a video or two on it. So we will be doing another video on this at some point in the not too distant future. Apologies for the plugs, but at the end of the day, a free scope is something not to be sniffed at. As always, thanks ever so much for watching Dubious Engineering. Take care, have a wonderful week and weekend, and we'll see you again soon. Don't forget, give us a good old thumbs up, subscribe if you haven't already. Cheers and beers, people. Bye for now.